So we will be waiting few more minutes and after that we will start today's class. Have I guessed this one? Okay, so we will start today's session. So good afternoon everyone. So I am Niloy, your TA for this course, Conduction and Convection Heat Transfer. First of all, I would like to welcome all of you to this live interacting session. So this is our sixth live interacting session. So we have previously completed the fundamental concept of this conduction and all this thing, and I hope that all of you have gone through the course and which has been taught by Professor Chakraborty and Professor Shom. So this is really a good course. So I hope that all of you are enjoying this course. So before starting today's session, so first of all I introduce these courses to all of you, why this courses is necessary and why you should study this course. Because this course of this conduction and convection heat transfer, so that you will find in your daily life problem. If you talk about this engineering problem or any biological problem, so each and everything you see in your daily life, you can relate it with these types of conduction and convection problem. Also say in our daily life you see that if you are in your body, if you are feeling fever, so your body temperature rises and all these things you can correlate. So we are basically dealing with this fundamental concept along with this governing equation and the laws that defines this heat transfer mode. So that will be our motto. So already as we have completed the 5 sessions, so in this session what we will do is that we will initially introduce this transient conduction, which is mainly based on this semi-infinite slab. As in the previous classes we have dealt with this lumped heat capacity, so I hope that you understand this question. So this semi-infinite slab, the concept is somehow similar to the previous concept of this lumped heat capacity. So next is that we will be coming to this concept of the convection, though we have already discussed a little bit about this convection, but now we will study in details about this convection, how the convection depends on various types of fluid properties. So that's why though it's a course on this heat transfer, but we will also study this fluid mechanics. In these courses, we will deal with both of them to define how each and everything is correlated with each other. Like if the fluid property, in a certain fluid property, if you talk about this density or viscosity, how it is going to affect your convection heat transfer. So all these things we will be going to study. So we will start with this problem of this transient conduction, the semi-infinite slab. Okay. So if you are while this session, if you are facing any issue, you can switch on your mic and you can tell, or you can also write in the chat box. Okay. So the first is the 1D unsteady. So it is clearly written. It is heat conduction through infinite slab. So this is the topic we will discuss today. So for infinite, let's say let us assume this is an infinite slab. So well, where in the if I talk about its axis, so this is infinitely long, even the bottom on the top side, but its thickness is somehow constant. Say this is the same thing. I think that you have also found in this course, right? This is twice L. So I just represent it in axis y. Okay. So in axis y, say this is your x-axis, this is your y-axis. So in the y-axis it is quite long, or you can say it is infinite. So in the x-axis we will be only dealing with this x-axis, right? So I am just giving a temperature condition like that. Here the temperature, say the temperature is T0. Also the here the temperature is 0 or T0, right? So certain types of condition it may gives. So the boundary condition is depends upon the it may vary from problem to problem. Like say for your better understanding, I am just representing it T naught. Okay, not 0, it is T naught, the initial boundary condition. So I will be using as it is an 1D equation. So this 1D conduction equation, you know what is it? So first I consider this K as constant. So why 1D not because in this y direction, as we have already considered it infinite. So if you talk about this equation, so which is q gen by k, this equal to 1 by alpha del t by small del t, right? This is the equation. So say for your understanding, I just take two things. The first is in the x direction. Say in the x direction, it should be in the y direction. It should be like this, right? But as I have said that in the y direction, this is infinitely long. So if you see the temperature at this point is T naught, so it is also T naught like this way. Only we will be dealing with the temperature variation along the edge. So we will not be counting this thing. Also, let us assume this Q generation for this problem be 0. For this only this problem, we are just assuming this thing. So that means we just assume this thing. Okay. So this equation is getting converted into this format. Up to this, any issue? So why it's an unsteady problem? Because there is the term change in temperature with change in time, that is del T, capital del T by small t, right? So that's why this is how this equation is coming, where alpha is your thermal diffusivity, right? So more realistic, I just do one thing. So it is in, as I've initially written it as 2D form. So that's it should be partial. So you can write it in partial form or single form. It is not a problem because already we have ignored this thing. Okay. So it's up to you because it's a single 1D. So you can take the partial derivative or also you can take the you can take the partial derivative. So that is it. Okay. Now we have also studied in the previous class how to solve such types of equation. So we can we can take a function, two different function t as a function of f and g. In the previous class we have also done this thing. This is the similar thing we will deal here, right? So before this we just assume, let this t be, sorry, this theta be t minus t naught. Okay, so that is our assumption, right? Okay. So what is the boundary condition here? That is important. So initially it's like for our understanding we just convert this into theta as t minus t naught. So now this is at origin and we have seen that why we have taken the axis in the middle one, because this is symmetry. Say here t equal t naught, here similarly, that means it's a symmetry problem. So at this symmetry problem, the boundary condition, if I am talking about this boundary condition, what it should be? So the first boundary condition should be that at x equal to 0, it should be, its gradient should be 0. So that should be d theta by dx, that should be 0, right? Okay. So next boundary condition can we say at L, plus L or minus L. So I am taking plus L. What is it? It should be 0. Why? Because at boundary this is T naught. So this will be, theta will be theta L. I can write. So theta L means T naught minus T naught, which is 0. So that will be your boundary condition. So the main motto is that you should know the boundary condition here. So which is quite important. Okay. So now as I have replaced it in this form, so I can write now in place of t I can write d theta dt. alpha d square 3 by dx square. So I hope that it is clear to all of you. Now what I do, I just take this theta, say it is a function of f and g. So see, if you look into this equation, here two variables, one is temperature and one is x. So that's why I have to write theta as a function of time and x, space coordinate and time. So that means you have to write this theta, which is the temperature profile, as a function of the space and a function of time, or temporary variation you can say, right? So up to this it is clear. So now if I just do the first, so d theta by dt, if I take, so it should be, that means here fx is a constant because it's a derivative of this one. So I can write, so in short I just write it at fg dash. Okay. Similarly, the double derivative of this theta with respect to x square. So what I will get here, g is the constant and it should be the double derivative of f, right? So this equation, just a minute, let me write down this equation. So I can write now this equation in this form. In place of d theta by this one, what I can write, the equation should be f g dash equal to alpha f double dash g, right? So more realistic, I can write f double dash by f. This is 1 by alpha g dash by g. So see, in this way, I just, where the theta initially was a function of x and t, but now I just split it into a two separate function of f and g for my simplicity. Okay. So if you see this first part, if I'm talking about this first one, the first part is only a function of your x, right? Whereas the next part is only a function of t, because here this alpha doesn't depends on x or t. So that means clearly it is a, we have separated it out, right? So yeah, if it is okay, then we'll move to the next part. Okay. So in the next part, in similar types of question, what we need to do, like you have done in the maths, so we just assume each part as minus lambda square, right? So I am erasing just this part. So that means I can write f double dash by f, this is minus lambda square, the next is 1 by the g dash by g, this is also minus lambda square. Okay, so now I can easily solve this one. Say if I want to solve this one, so what basically it is 1 by alpha g. G dash basically means it's a derivative form. So that means it is like this format, right? So again integrating with respect to t, so what I will get, so if you integrate you will get this thing. So this dg is minus dg by g. This is minus lambda square alpha dt. So integrating I will get ln g into minus alpha square t plus ln c1. So that means clearly I will get g due to c1 e to the power minus lambda alpha square t, right? So this is the thing I will get from here. So this is the value of g. So now I know that the theta is a function of f and g. So I got the g, only I need this value of f. So similarly you can find out this f, right? So this f is already this thing we have done in the previous class, so I am just writing. So this is that format. So in such types of equation, what is the function? That is c2 cos lambda x plus c3 sin lambda x, right? So this is how you can derive this. So now you have this boundary condition. So what you have? You have this boundary condition and this boundary condition. So if you put this boundary condition here, so you can easily get the solution, right? Say if you put at x equal to 0, here at x equal to 0, this means cos 0, which is 1, and this one is 0, right? So that means here this is c2, function will be c2. So again what I have said that theta is a function of f and g. So as theta is a function of f and g, so f is a variable of x. So it will we have to take this c2 is 0 for f equal to 0, only it is possible if c2 is 0, else it will be a trivial solution, right? So that's why you can easily get this value. So that equation easily you can write as c3 sin lambda x like this way. So and also few more boundary condition can be provided in a given question. So based on this you can easily put this g, which is c1 e to the power minus lambda square t alpha into c3 sin lambda x. So this is how you will get a solution. The main motto is that initially you need to find from this problem, you need to find the 1D unsteady conduction equation, which I will get this way because I have assumed this your heat generation V0. So and after that what I need to do, I have just need to convert this theta as a function of time t minus t infinity, where t is the temperature at any point in the domain, right? So that thing I have done, and additionally as you see this equation, this differential equation is a function of time and x. So that's why I just write theta as a function of f and g. Okay. Then what I did, I just derivative this and just convert it in terms of f and g, and we will get this solution, right? So this is for an infinite slab where for a conduction, right? This is for infinite 1D unsteady state heat conduction through an infinite slab, right? I am moving to a next problem. So up to this any confusion, please let me know. Okay. So this is how you need to solve such question. Like this is a certain question. If the question, so I am erasing this thing. Say it a given question. I am just using another color for your understanding. This color. Say in place of this, if somewhere it is given the heat is flowing, this is given like this way. Here the velocity is flowing with the u velocity. Like this way it is given both sides. Similarly on both sides it is given h and t infinity. So what is the basic motto? So that equation, the first boundary condition should remain same, but the next boundary condition would change. Say at x equal to L now, what it should be? This should be h into t minus t infinity, right? In this way you need to do. And another thing is that this theta in that case at this is t infinity, so this is also your h theta. So this is the new boundary condition for a convection. Rest all other things are same. So see the all the derivation where I have get the theta equal to this one up to this it will remain same. Only the condition is that you need to understand the boundary condition. That is the basic difference. Okay. Now I am moving to this your convection. So why convection? We will today deal with this convection in details. Okay. So why this convection is important? The next is your convection. So what basically is convection? Already you know that the convection is a mode of heat transfer which basically because of the motion of a fluid. Okay. So only not because of the motion of the fluid. Say in the past classes I have said that convection is not a you as you have gone through these courses you will get to know that the convection is the primary mode of heat transfer, but the convection is basically, if I write, it is basically conduction plus fluid motion. Fluid motion. So that thing you can say fundamental, but in fundamental case what type of convection? So that convection basically is your molecular conduction or diffusion. So it will be done at the molecular level. If it is a surface and here the fluid is flowing with the u infinity, h, t infinity. So there are certain molecules on this wall. How they are diffusing the heat, that is important for convection. Okay. And for the fluid motion, this term is known as advection. So this is a combination of both these two. So what will happen? Advection basically means here as the fluid is moving, so this particle is transferring it to the next one and it is continuously moving. So in this motion it is taking up the heat. So that types of heat transfer mode is known as the convection. So it's a combined effect of conduction within the fluid and the fluid motion. So you see what I have said is molecular conduction is because they are the molecule of this at the interface or the from the interface to the fluid. So in each of the fluid molecules there is certain conduction. So that conduction is also considered in case of convection. So convection is not a solo heat transfer mode, it depends on conduction plus fluid motion. Okay. So if you see this fluid particle near the surface, so what happens to this fluid particle as the conduction is going on? So either it will gain heat or it will lose heat. So there may be two conditions because of the conduction two things can happen. One is it is releasing heat, another it is conducting heat. Okay. So say if it is in heated plate and fluid or this particle is moving like this u. So what will happen? So this heated wall will reduce its heat. That means it will cool. This is because this fluid particle here near the surface of the fluid will be moving away by this fluid velocity, and because of this new particle will come into this place. So previously it was this purple color fluid particle, and after a certain time this purple color fluid particle will be replaced by other fluid particle. Say it is of green color. So this is the new particle, it will come, and again because of this conduction it will take up this heat and it will again flows and new particle is again coming. So this is how this fluid motion helps the surface to get cool. And already you have said the new this molecule basically represent the new fluid particle, and this process will continues unless and until the liquid gets certain amount of heat. Okay, so this is the fundamental concept of your convection. So types of convection, if I talk about, there are two types of convection. Okay, so before starting into this types of convection, no, see if this is a solid block, right? So if you know the temperature difference T1, T2, and this is U T infinity H, and there is flow. Okay. So and there is no other heat loss, no heat generation. If I say Qgen equal to 0, and it is in steady state, and also it is in steady state. So what that basically that means the heat conduction because that means the heat transfer due to conduction equal to heat transfer due to convection from this energy balance equation. So what it would be then? Then the equation would be like K A means the surface area, K A del T. So which is basically your T1 minus T2. Sorry, this is your T2 minus T1 by, if this one is your L, length is L, so this one is L, which is your H A T2 minus T infinity. Let us assume that T2 is greater than T infinity. So in other word, if the area is same, so this is K U T1 minus T2 by L H T2 minus T infinity. So right, so this is the thing also you have studied in the earlier. So similar concept you need to apply to solve numerical problem, right? Okay. So how many types of convection are there? Basically, there are two types of convection. The first is the natural convection. So the first, what is natural convection? Here basically the fluid motion occur because of the buoyancy force. Why? Why the buoyancy force happen? Say in a fluid. So certain say there is a fluid. So if you are supplying heat from the bottom, so this vessel you are supplying heat from the bottom. So what will happen? Initially this fluid will heat up. So what will happen is density will reduce. So it will move upward. So colder liquid will come place. That means there is density difference, right? So this is mainly because the buoyancy force is happening because mainly of density difference. So which one is less denser? So as I have said that initially this is your hot fluid, right? So this hot fluid means your density will reduce. So this fluid will move upward. So that means there is fluid motion. So indirectly there is fluid motion and this is mainly because of the fluid density. So we also know that the high density fluid moves into this low density region. So that's why it is moving upward, right? So similarly now this as this hot fluid moves upward, so this cold fluid will comes to take its place. This is your cold fluid. And what we know, the temperature of this the cold fluid basically means the density is more, so E2 will goes downward. Okay, so this is the concept of this natural convection. So indirectly we can say that it is basically because of temperature difference, not only density difference. So because both these terms are correlated with each other. Because if the liquid at the bottom first heated up, its temperature will be more than of the top liquid. So there is temperature difference. Also you can say in terms of density difference, this is same thing. So now if I talk about this example of this free convection or this natural convection, what we have is huh. So if I talk about the room, in a room during the winter we are using heater, right? So the heater radiates from the heater, the surrounding air first gets heat up. So and after that it will circulate in the room, and the colder fluid comes to the near this radiator and it will near this heater. Sorry, near this heater, and this again heats up until and unless the room achieves a certain temperature. So similar is the concept of AC. So if you talk about this AC, so if you set it outside room temperature is 30, if you set it at 25 degrees centigrade, so what it will do? It will initially cool the certain amount of air near to this AC, and again it will circulate. The hot fluid moves, and this process is continuously going on until and unless the room temperature moves to 25 degree. Okay. So that is the concept of your natural convection. But in real life, this natural convection, if I talk about this natural convection, also Also, you can see this natural convection phenomena is also happening in boiling water. If you have started to boil water, you will see certain types of waves like thing appears in this water before you see this bubble, right? So this wavy nature is basically because of this convection current. So this is your convection current, which indicate that this water fluid is moving upward, this colder fluid is moving downward. Because of this, you can see these waves, right? Any confusion up to this? So we will wait 1 minute before starting into this force convection part. So this force convection. So now we will be starting with this force convection. As you have studied this natural convection, this force convection is not that much tough, but it is quite essential for research point of view and for daily life problems. So here the fluid motion is mainly produced by external device. Like if I talk about this cup of tea, in the if you from the cup of tea, if you pour this tea in a plate, so it will, if you just keep it at room temperature, though it will cool, but it will cool because of only natural convection, right? But if you talk about, if you are in a hurry, so you need to cool it a quicker time. So what you do, you are just blowing air from your mouth. So because of this blowing air, it will cool faster. That type, because here the flow is fluid motion is mainly from an external source. So that's why it is known as forced convection. So in your real life, you see that fan are used to cool something, or this pump is used to flow water, right? Even blower is used. So to dry this hair, people are using blower. So certain things, wind, if wind is also a forced convection. So it's a natural phenomena, but it's an externally applied thing to a certain heated surface. So that's why we are considering this as a forced convection. So okay. So is it clear? Now we have studied also this Newton's law of cooling. What it is basically if you talk about this Q, heat transfer rate, which is your HA, surface temperature minus T infinity, is the fluid temperature. If this is your surface, this is your Ts, and this is your fluid temperature T infinity. H is the heat transfer coefficient or the convective heat transfer coefficient. So this thing already we have studied. So I am just recapping these things because that will be necessary to solve a problem. Okay. So now we will be moving into few problem. So No question till now. Okay, so please read this question. I'm giving you 1 minute to understand this question, understand this problem initially, and after that we will start. Okay, so you have studied this question. What is it? So it is given a cuboidal transformer of edge length A equal to 9 mm and mass is given Cp is given heat dissipation is given as 6 kilowatt 6 watt, sorry. So and is ambient air temperature is given 43, H is given. So many of the thing is already given. So it's a simple question, right? Why? Because if you talk about this question, just remember one thing. H is given, which is your 25. I'm not writing the unit, right? P dissipation, that is basically your Q, is given 6 watt. Already unit is in watt. So next what they have given, T infinity is given 42. So gradient, no temperature gradient exists within the transformer. So that means basically they are talking that no conduction is there. No temperature gradient means no conduction is there. So only the heat transfer mode is because of this convection, right? So so what is the question? Next question, say in the question another thing is that as it is a cuboidal surface but the bottom of the surface is insulated. It is quite important. Bottom of the surface is quite important. Just remember this thing. So steady state temperature there. So as it is a steady state, we know that the previous thing. This is the heat dissipation. So this heat dissipation basically is because from this energy balance, I can say that this heat dissipation is mainly because of convection, right? Okay. So which is basically your H area into T minus T infinity. So you need to find this T. So for this H is already given, it is at 25 most probably. Yes. And T infinity is, we need area. How to find out this area? It is given, it is a cube having edge 9 mm, but the important thing is that one of its end is insulated. So how many phase? A cube has 6 phase. So how many phase is involved in heat transfer? 5 of the phases is involved in heat transfer. So basically it will be, the area is 9 mm most probably. So I have to convert it into, right? So this is the thing you will get. So solving, so just calculate it and just put it here. Every value is given, you will easily get the answer, right? I think someone has answered it. Let us check. Yes, Purvo has answered A. Option A. Let us check. Yes, it's a correct answer. So I'm just solving it for others. So it is basically you will get it as 4 around it is 4.05 into 10 to the power minus 4 meter square. So I have to put it here. So already the distribution is given as 6, right? So t minus 42 t infinity. So if you solve, you will get Ts as 634.6 degrees C, right? So the correct option is option A. Good, Apurva. Next. So similar types of question is also given. Please solve and let me know what is the answer. So I'm giving you 2 minutes time. So please solve and let me know the answer. So someone has answered. Yes, it's option B. Yes, yes, it is correct. So this is nothing. Here only the changes is that if if the surface that is insulated, if it is not insulated, so what will happen? Only then the area will change, which will be 6 into a square, and rest thing will be same, P distributed equal to H A T minus T infinity. So you can put, and accordingly you will get all this value, which was given as 625. Area you can find out. And solving you will easily get this T, which is coming as 535.8 PC. So the correct option is option B. So this is a similar types of question. Okay. So I hope you understand. So why conduction is not there, that is important here. The conduction is not there because here it is given that the in spatial, that means space, with respect to x, no temperature x or y, with no temperature gradient doesn't exist. Okay. So that is conversely correlate equivalent to no conduction. So I am moving to next concept. So age. Now what is age? If you talk about this age, we know that it is heat transfer coefficient. Okay. But if someone asks you the definition, what you will say? So conversely, I can write now H as Q by A T minus T infinity. So then what is H, convective heat transfer coefficient? So it is basically the rate of heat transfer. This is the rate of heat transfer now. So but where the rate of heat transfer, this is from a solid to a liquid. The H basically means the rate of heat transfer from a solid to liquid per unit area. Area should be perpendicular here, right? Not perpendicular required, but area should be generally perpendicular, and also per unit temperature difference. What temperature difference? The temperature difference is basically the temperature difference between the surface and the liquid. Okay, so that is the definition of H. So is the rate of heat transfer from a solid surface and a fluid per unit. Unit means if I consider the area as one, per unit surface area and per unit temperature difference, and per temperature difference. So that is the definition of the convective heat transfer coefficient, right? So the important thing is that you see here, if you observe here, the heat transfer is mainly in case of convection is happening from a solid to a liquid. So what is important? The fluid flow is important here, because how the fluid is flowing over the solid surface, that is also important. So we need to understand. So thus we need to understand how the presence of a solid surface affect the fluid flow. So that is important. So generally what we have observed, say you have studied this fluid mechanics, if this is a solid surface and if the fluid is moving here, so what you observe that just on the surface the fluid motion on the surface, that means this fluid particle here, the fluid motion of this particle is almost zero, right? So what we can say that this fluid particle is not moving, though the fluid has certain velocity. So such types of condition is known as no slip condition. So why such types of things? This is because there are molecules, like water molecules, stick to this surface, and somehow because of this viscosity or other property, this particle gets stick to the surface and it only release unless after it gets some certain amount of velocity or certain amount of momentum, without which it will not release. That's why this velocity of the particle near this solid surface is zero, and that types of condition is known as no slip boundary condition, right? So this no slip boundary condition is quite important. So for your understanding, just I am drawing a plate. So this thing you have studied in fluid. Say I am supplying uniform velocity before this plate. Okay. So let the velocity be your u. Okay. So what will happen as it comes to the solid surface? Initially at this point the velocity is zero, and after that its velocity is increasing, and it will increase up to a certain level, and after that it will almost constant. Why initially it was such that initially because there is zero bound no slip condition. So this is your profile. Okay. So the velocity at this point is zero. So or we can say that the relative velocity is zero, right? Generally, if I talk about this viscous gradient, so viscosity, like if I talk about this heat transfer or the heat flux, because of conduction, it is equivalent to your temperature gradient. Similarly, if someone talks about your viscosity, it is equivalent to your velocity gradient. So remember this thing. If there is no velocity gradient, then there is no viscosity, but here you see that the velocity changes, so there is definitely velocity gradient, so there is viscosity. So that is another, this one is correlated with each other, please remember this thing. Okay. So where, so in a above a surface, if the fluid is flowing, so from the region up to the region where you will observe that this there is velocity gradient, so these types of region is known as your boundary layer. Okay. Say up to this you can see that after this there is no velocity gradient, but below this there is velocity gradient. So similarly, if you take, if we talk about certain particular, sorry, say if you take again at this initially this temperature gradient, initially you can see the temperature gradient will follow. So the profile will change. This profile will change. So sometimes this profile should be like this also. These types of profile you will also observe. Okay, so it will maybe it increase or it may decrease. So certain profile, this profile will change, right? So based on this profile, this boundary layer is forming. It is basically a layer up to which you will observe this velocity gradient. Okay, this is known as the boundary layer. So if someone asks what is the property which is responsible for your nose boundary condition, you will definitely say it is viscosity. Similarly, if someone asks why this boundary layer is forming, you can say that it is because of this fluid property which is the viscosity, right? So more details is there. We will come into this after few notes or few questions. Okay. So let us solve few question again, and after that we will move to few fundamentals. So please read this question. I am giving you 1 minute. Okay, please read this question and try to solve this one. So you have read this question. Okay. So there is a little mistake here in this question. Let me correct it. This is your 27. Okay. So this is the question. So first see what is given in this question. That is important. So the diameter of the tube, diameter of the wire is given, and also its length is given, right? So insulation. It is its insulation is given, right? So these are the things that is given in this question. So apart from this, what is given? So the current of the electricity that is flowing here, it is also given. Okay, so voltage and current is given. That means the heat generation is given. Indirectly, I can say that the heat generation is given. So the insulator wire is exposed to a medium. So I am just drawing this scenario for you. So initially, this is your wire. Okay, so this is your wire. Wire voltage and current is given, right? And above it there is an insulation layer. Say this black line indicated this insulation. From there to there, it is insulated. Okay. So it is exposed to atmosphere where T infinity is given as you 27 degrees centigrade, H is given as 20 watt meter square Kelvin. Hmm. So it is given 1 day steady state and all these things are given. So the first question, coming to the first question, what is given? The rate of heat transfer from the wire. So this is simple question. So as they have asked about this rate of heat transfer from the wire, so 1 day steady state equation. So either there is conduction, convection or heat generation, right? So the heat transfer, but here clearly it is mentioned that the electrical measurement indicate that a current that passes through the wire and there is voltage. So this is the heat that is already generating in the system. Okay. So the heat generation in the system, the rate of heat, so whatever may be the heat generated in the system, that will be only transfer. So this Q basically is V into I, right? So which is your V is given 10, I is given 9. So basically 90 watt is your required heat transfer. So that is a simple question. So the correct answer is option A. This is your 90. Right. I hope that you understand this thing. Now I am moving to the next question. The next question is the convective heat transfer resistance. So the next question is the convective heat transfer heat transfer coefficient. So please try to solve this. So the convective heat transfer, sorry, resistance, not coefficient. It is resistance. So just I am giving you a resistance mean R convection, which is 1 by HA. So it's a simple thing. So you need to find this thing. H is given here. So only you need to find the area. So what should be the area? So please calculate and let me know. I'm giving you 2 minutes, 2 to 3 minutes time to solve this one. Okay, please check. Okay, let me solve this for you. So in this question, what is given? So diameter of the inner diameter of the wire is given as your 3 mm. So as the area, which area will be calculated here? The area means the area that is exposed to atmosphere, that is the outer area. So the d outer should be your, so to find out, it is having 1 mm thickness on both sides. So that means it will be 3 plus 2 mm, 5 mm, right? So you can easily calculate the area. Area is equal to pi d l. So pi is given as 3.14. D is given your 5 mm. So 5 into 10 to the power minus 3 into L is 10. So it will be 7. 15.7 into 10 to the power minus 2. So which is 0.157 meter square, right? So H is already given as your 20 into 0.157. So if you calculate, you will get 0.318, like this, 0.318. Let's see whether such option is there or not. Yes, option B is there. So the correct option is your option B. So I hope that it is clear to you. So option B is your correct answer. So next I'm moving to another question. So which is basically on the thermal resistance offered by this plastic. That means insulation. They are talking about this insulation, how much thermal resistance. So what is the heat transfer through this plastic? The heat transfer through this plastic is basically because of which mode of heat transfer? Because of conduction. So indirectly they are talking to find out this conduction heat transfer resistance. So it is also quite easy. Again, I am moving to this part. So it is a cylinder. In this cylinder, you need to find out this thermal resistance offered by this plastic, or this thermal conductance resistance. So I hope that you remember this formula of thermal conduction resistance. So please try to solve this one. I am giving you 1 minute time, and after that I will solve this one. Okay. So in this question, what has been asked? So the thermal resistance offered by the plastic. So this is the thing they have asked you to find. So what is the formula? Because it's a cylindrical surface, so I know that for a cylindrical surface the conduction formula is ln R2 by R1 into 2 pi k into L. So this was the formula. Just put the value here and you will get the answer. This is as simple as that. Okay, so please put this value and let me know what is the answer. So I am writing again this formula. R conduction is ln R2 by R1 into 2 pi KL. R1, R2 you know. Diameter 1 is given as 3. So R1 should be 1.5 mm. R2 should be 5 by 2, that is 2.5 mm. Right. So the K was given as 0.2 and length is given as 10 meter. As simple as that. Please solve and let me know what is the answer. So the correct answer is 0.0407 you will get, which is option A. Okay, I think it is clear to you. So I hope that this is clear to you. So okay, so please next question. So please find the total thermal resistance. It is quite simple. Because you just add these two resistance, nothing else is there. So here the solution should be R convection. So R plastic means R conduction. So I have just write this. I have just so it will be option A. This is correct. So it is 0.407 and the previous one is 0.318. Okay. So this is your 0.0407 plus 0.3185, which is your 0.3592 kilowatt. Okay, so this correct option is your option D. Okay, so few more question. So the next question is that what is the interface temperature? So I am again moving to this question. So in this question, what has been asked? So you are asked to find out this interface temperature, right? Just a minute. Let me erase this thing. So the question is that this is the main question. So in this question, it was asked to find out the interface temperature. Okay, so that was the question. So how to find out this interface temperature? So to find out this interface temperature, you need to know this fundamental concept. So as this is an wire, so as I have already said this wire, so what happens, the current is flowing and the voltage is flowing. So basically the heat supply, you know, this Q is given, which is Vi, and we have already calculated it as 90 volt, 90 watt, right? So this is the heat generation. So what I know that the heat should be equal to this, and also it is given an insulating layer over this wire. So because of this insulating layer, and it is given a thermal heat transfer coefficient is given. So H is given as your 20 and your T infinity is given as 27. That thing I have already discussed, right? So this heat, whatever the heat is flowing inside this wire, so this will be transferred because of conduction through this insulating layer. So some amount of heat will be lost, and whatever be the heat transfer here, that will be lost to this atmosphere, which is your convection, right? So the Q is given 90. So conduction, because already in this question, see one thing, we have found out this thing. And next question we have found out this convection heat transfer resistance, right? So convection heat transfer resistance we know, conduction heat transfer resistance we know. So I know that Q is temperature difference minus, say this temperature difference as Ts, okay, and this is your T1. So this conduction means T1 minus Ts, right? And below is your R conduction, and the atmospheric is at T infinity. So there should be your Ts T surface minus T infinity by R convection, right? Just I need to put the value. This is 90. T1, I need to find out this T1. Ts, T conduction, you know. What is the T conduction? This is your 0.0407. Already I have calculated this one. Similarly, this Ts or T infinity. So we need this T infinity, which is your 27. R convection also we know that this is 0.31847. So these two, if I take these two, we can solve easily. 90 into Ts minus 27 by 0.31847. So correspondingly I will get Ts, which will be your 55.7 degrees centigrade, right? So similarly, if you use after that you can solve these two. So and you will get this T1 or the interface temperature. T1 basically means interface temperature. What is this value? So you have to calculate and you will get the temperature as 59.3 degrees centigrade. Okay. So this is your option C is your correct answer. So I hope that you understand this. Now it is the critical radius of the plastic insulation. So it is quite simple question. So please, I am giving 1 minute. So if I talk about this critical radius, so we have already studied in the last class that the critical radius is K by H, which is the, so which we have studied for the insulation, not in the last class, last two class back. We have studied about this, where K is the thermal conductivity, H is the heat transfer coefficient. Basically, it it indicates how much this conductive heat transfer and how much convective heat transfer is taking place and what is the radius required for this. Okay, so in order, so this is the minimum critical radius, so that radius must be there, so to avoid further heat losses. So that much that this K value or the H value is proportional. That means if I take this, if I put this in radius, then the heat loss will be comparatively less. So you just put it here, this value of K. So this value of K is your 0.2 most probably, and this one is your 20. So that will be your 0.001 meter. So the option is in millimeter. Sorry, 0.01, not 001. This is 0.01 meter. So accordingly you can get the answer, which is 10 mm. So the correct answer is option B. Okay. So next question. So in this question it was asked about this Biot number without this plastic insulation. So Biot number, basically if I talk about this Biot number, so Biot number is basically HL by K. So it is talking about without insulation. So this is characteristic length. This is insulation of the oil. This is the thermal conductivity of the wire, right? So H we know H is 20, and L we need to calculate. L basically is your V by area, LC. So it is a wire. So the volume should be pi 2 pi r h. Sorry, this is your pi r square h, right? And this one will be your, this is the outside layer, so this one is with 2 pi r l or h. So ultimately you will get this as r by 2. Okay, so this will be your r by 2. So you can find out this value, right? Now you need this K of the wire, thermal conductivity of the wire. What is the thermal conductivity of the wire? You need to check in this question. What is the thermal conductivity of this wire? One important thing is that, just a minute. So this R, what, which R will be even, this is your inside radius. So this R will be your 1.5 mm R, right? So basically this will be your 0.75 mm. Now I have to find out this K wire. So let's go to find out this K wire. It is whether it is given or not. So the K, what is the, whose thermal conductivity? Plastic cover, whose the thermal conductivity of the plastic cover is given, but nowhere in the question the thermal conductivity of the wire is given. So we can't be able to solve this question because of insufficient data, right? So K wire is not provided. So the correct option will be option D, because the data is not provided here. K wire is not provided. Okay. So that is because of this we are not able to solve. So similar, last one question, and after that we will discuss a little bit about this H. So this is a similar question. So this is with insulation. So again this is same, just a HLC, but this time the K should be that of insulation of the plastic, right? So H is your 20 already know. So you need to find out this LC. So this LC basically is R by 2 we got, but here this R should be 2.5 by 2 because it is the outside radius. So that is 1.25 mm, right? That is your 1.25 mm. So I have to convert it into meters. So that will be 0.00125 meter. So 0.00125 meter, and K I have got as 0.2. So if you solve this, you will get the answer 100. That will be 0.125. So the correct answer is option B. So I hope that it is clear to you. Okay, any confusion up to this numerical problem? So now we'll move to some fundamental question. Not fundamental question, sub fundamentals of this convection and convection heat transfer. Okay, so how they are correlating with each other and why they are important. So there is a skin. So in this skin I am just showing. So now I am talking about how this heat transfer coefficient. So Nusselt number, now I am talking about this Nusselt number initially. What actually this Nusselt number is? So Nusselt number basically, if I talk about this Nusselt number basically is this, whatever be the heat transfer due to your convection by heat transfer due to conduction. So that thing gives you this information. So the heat transfer through the fluid is basically because of your convection, right? Why it is so? Because there is fluid motion involved in this, and by conduction, what is happening? The fluid layer and there is conduction when because the particle from the solid to the fluid is traveling because of this conduction. So that is the scenario. So how much the convection is taking place with respect to conduction, this thing is been given by this Nusselt number. Okay, so which is basically your H delta T by K delta T by L. So you see that certain types of way of derivation this thing has been given in the in your book. So that is how its one form. Apart from this, there are certain other forms. So which you will find in your in the lecture as given as you can find the derivation given by this Professor Chakraborty, right? So that thing also you can have a look. Just a minute. Just a minute. I am giving you this in. Say whatever. Say this is a plate, right? Through this plate, the heat is transferring. So this plate has K thermal conductivity, and the heat transfer is taking place in the X direction, and also there is liquid flowing. H is there, H is given. This is your T infinity. So what I can write? I can write this formula from this energy balance equation, del T by del, say in the y direction I am taking. This is some certain thickness. Now I am taking only in the y direction. This is your y direction. So del T by del y. So there should be your equal to at a certain y1. There should be your convection heat transfer, which is T minus T infinity, right? So let us, I am just converting now this thing. This is your energy balance equation. Now I am converting this into non-dimensional form. So the what is the non-dimensional form of temperature? So this is the non-dimensional form. So the theta I write as T minus T wall. So basically what is going on? Just a minute. Certain issue is there in this equation. Okay, let us forget this. Hmm. So what is it? It is basically T. Your theta is your T minus T infinity. Sorry, T minus T wall. Say this is the wall temperature, right? By T infinity minus T wall. That thing I have just non-dimensional this thing temperature. Similarly, I have non-dimensional this y direction, which is y by L. Right, what is L is with respect to this thing, this is your L. So I made it non-dimensional also, so I just put it here, right? How? So you just need to derive this thing temperature if I just derivative with respect to y. So you d theta, what I do, if d theta that should be equal to into dt, right? Similarly, dy dash, this should be your 1 by L into dy, right? So now in place of this, can I write in place of d theta? Sorry. So I can write now in place of this one minus k, and here in place of this one it will be T infinity minus Tw into dt and into d theta. Similarly, here dy, in place of dy I can write L into dy dash equal to h T minus T infinity. So this one is getting cancelled out. So overall what I will get? I will get d theta d, this one is equal to HL by K, right? Any confusion up to this? So this is how we have derived this thing. Okay. So inversely I can say this is value. So this one value is your Nusselt number. So in other terms, I can say that Nusselt number is the temperature, is the non-dimensional temperature gradient. Yes or no? So basically my motto is to show that the Nusselt number is a non-dimensional temperature gradient, nothing else. So it is the non-dimensional, even non-dimensional temperature gradient. Okay, that's why I have shown this thing. So any confusion up to this? So I think no confusion. So next thing, so the next thing is that how the temperature is, how the heat transfer coefficient is varying with your with the fluid properties. Say this Nusselt number, basically this, if I talk about this Nusselt number, just a minute, screen, white screen. So this, if I talk about this Nusselt number, how this Nusselt number changes with this fluid property, that thing I will study right now. So this is the effect of individual fluid properties. I am talking about this fluid properties on convection. So today I will discuss with this term rho mu k cp velocity or L. You can write as u infinity. Okay. So this term I will study. So first, if I talk about this rho density, so what will happen? So this density. So density means higher density. If I talk about if the density is more, say for a certain scenario, this density is more. The density more means inertial force is more. So that means the stronger fluid motion should be there, right? So as there is a stronger fluid motion, that means the boundary layer is less, right now. So I have studied this is the boundary layer. So if you see boundary layer means the heat transfer, if the boundary layer is thick, so the heat transfer will be less, but if the boundary layer is thin, the heat transfer will be more. You have known, I have already discussed about this thing. So if the density is more, that means there is the fluid motion will be more. So if the fluid motion will be more, then the thermal boundary layer will be less, because with the fluid motion this temperature gradient will be less, so the thermal boundary will be less. So correspondingly I can say that this H will increase. If rho increases, H will increase, because boundary layer will get thinner. Okay, next is your viscosity. So see, viscosity is a quite important thing. So as I have told that the viscosity, what is the, why there is thermal boundary layer formation, this is because of viscosity. So definitely if the viscosity is more, the thermal boundary layer will be more. Boundary layer will be thicker. So if the boundary layer is thicker, that means that H will be less. Is it clear? Okay, I hope it is clear. So, so in the first thing, the Density, I have discussed about this density. Then I have discussed about this viscosity. So another see one thing. Those who are in the call, just try to answer one thing. If I talk about this conduction, or correctly I can say that if the temperature gradient is there is no temperature gradient, what does that indicate? Anyone? Anyone? Okay. So my question is that if the thermal gradient, if there is temperature, if the temperature gradient is zero, that means the heat flux will be zero, because the heat flux is proportional to temperature gradient, right? You have studied Q proportional to. Similarly, mu, if I talk about this mu is the velocity gradient. So both these things, remember, if somewhere in the fluid, if you see that there is no velocity gradient, that means the viscosity is zero. So please remember this thing, because each and everything is correlated with each other. Next is your thermal conductivity. So the thermal conductivity basically represented by K. So what is thermal conductivity indicate? The thermal conductivity indicate how much the heat diffuses into this fluid, right? So if the K increases, that means more and more heat will be diffused into this system. So if it is a plate, so if the thermal conductivity is more, then more amount of heat is transferred to this fluid. So if the more amount of heat will transfer, then the heat transfer coefficient will increase. The convective heat transfer will be more, right? Next is the specific heat. What is specific heat? First you need to know what is specific heat. So, so the specific heat basically means how much energy a fluid can carry per unit mass. So whatever, if I take a certain amount of mass of the fluid, so or how much energy it will carry with itself, that is indicated by this specific heat. So see, in this similar condition, if you observe this plate, so if it is releasing heat, so if there is a fluid which is having more specific heat, that means it is carrying out more heat. So at this fluid, for this fluid the H will be high. So if Cp is more, indicate H will be high, right? Next is the velocity. So velocity also, this thing you have studied in the first class also. So if the velocity is more, so I am talking about a cup of tea. So if you place a cup of tea, if you want to cool tea, what you do? You just pour the tea in a plate, and it will, and if you keep it exposed to the atmosphere, it will take certain time to cool, right? Now if you are blowing air over this plate of tea, what will happen? It will easily cool. So if the velocity of the, if the air that you are blowing, it has more velocity, then it will cool faster. So that means if the velocity of the wind, air or any source is high, it directly means that the heat transfer coefficient is more. Okay. The last is the characteristic length. So characteristic length, we can't say about this characteristic length what will happen. So if the, why I can't say what will happen? Say if the L increases. So if this is the characteristic length, so I know that the thermal boundary layer will increases with length. So if the length will increase, what will happen? The thermal boundary layer will be more, because the curve of the thermal boundary goes on increasing with length, right now. So if the length is more, so there is a chance then that the heat will reduce. But after a certain time, again their boundary layer decreases. So at that cases the H will be more. So we can't say until and unless the length of the boundary layer is given, we can't comment on this length. So the H may be high, H may be low. So we can't comment on this. So that is how this property helps in the heat transfer coefficient. So any confusion up to this? Hi Shashwat. So today I think you are late, most probably. Okay, 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 not an issue. You can have the video lecture also. So you can also check. So this is up to class. So you have some confusion, right? So this is the content up to for today's classes. So after that, you have few confusion. So I will solve this one. So please wait 1 minute. Let me wind up this class because up to this is your recorded session. Okay. So up to this. Okay. For these classes. So I think we will again join on the next class. So thanks everyone.